Hey guys, welcome back. Got an easy one for you today. We're just going to take what we know about confidence intervals and apply that to hypothesis testing. So we'll be using our example of the M&M's lab as well. So we always start out with writing our null and alternative hypothesis. So the null hypothesis is that there's no change or it's just a status quo. So in this case, it's like innocent until proven guilty. So we're going to assume that Mars and Mars claim that there's 20% orange M&Ms is true until we have enough evidence to call BS. So we're going to for our null hypothesis, we're going to say the true proportion is 20% orange. Then the alternative is that there's going to be a change. Now, it's either a one-sided or one-tailed alternative test, or it's two-tailed. Now, in this case, it wouldn't matter if it was more than 20% or less than 20%. Either way, we would be able to call BS. So oftentimes it's only only one direction, but we're going to go two-tailed test in this case. So we're interested to see if the proportion is different than 20%. Whether it's higher or lower, we'd be interested. So our next step would be to select an alpha level. So we have several different alpha levels that are usually used. We have 1%, 5%, and 10%. Now the default is to always just use the 5%. It's kind of like the Goldilocks happy medium. But if it's really critical that we don't make a type 1 error, which is when we basically call BS when we shouldn't have, like a false positive is another name for that one, then we would set an alpha level, a really high burden of proof of 1%, meaning that we would have to be in the top 1% of sample proportions in order for, if the null hypothesis was true, in order for us to be able to call BS. But typically we use 5%, and then 10% is kind of sloppy, but we can use that in this case because we're just talking about candy. It's not life or death. There's nothing super critical. If we got it wrong, yeah, we might look like a jerk, but it's not that big of a deal. All right, so our sample proportion was 28 out of 114. But that was just one sample, and we expect the samples to vary, right? And so it's just if this sample was in the top 5% of samples that we would expect, then we would be able to call BS. Essentially, that's what's happening with our significance level. All right, so the sampling distribution model is based on the assumption that the null hypothesis is true. So if the null hypothesis is true, which is that we actually had 20% orange, then what's the probability of getting a sample proportion of roughly 25% like we did? Well, that was, I think, around 9%. It was like 9.8%. We can actually find that if we want to, but basically the sampling distribution model, or the distribution of all sample proportions, would actually be based on the 20%. So our P naught and our Q naught, which is our hypothesized proportion, and Q naught is going to be the 0.2 times 0.8. Okay, so it's not using our sample proportion, it's using the actual assumption that the 20% is actually true. So then divide that by 114, take the square root, which will give us a sample distribution model standard deviation of 3.7%. All right, so if I want to put this in the calculator to find the p-value, I'll show you how to do that. We're just going to go to stat, arrow to the right to test, do a one proportion z-test. The hypothesized proportion is 20% orange. We had 28 out of 114. And then we want to know if the proportion is not equal to the hypothesized value. So it's not a one-sided test, it's actually a two-sided test. And then we'll hit calculate, and that will give us our p-value. Our sample proportion is given, our p-value is basically 22%, meaning we had roughly 11% on both sides. So we were in the top 11 percentile, but it is actually a two-sided test because we go from both sides in this case. And so because our p-value was, we would expect to be that far away, that z-score or further away, roughly 22% of the time, which is pretty common. And so we're just going to say that was too close to call. I mean, it would likely could have just occurred by sampling variation. We believe it actually probably still could be 20%. And so we didn't have a large enough sample size in order for us to be able to say, because it actually could be 24% instead of 20%. We just didn't have a large enough sample size to be able to conclude that with any degree of certainty, essentially. All right, so what we can do is actually test these hypotheses with confidence intervals as well. So what we're going to do is build a confidence interval around our sample proportion. So I'm going to take those values that I had and create a confidence interval. So I'm going to go to stat test, one proportion z interval. We had 28 out of 114, and I want to do, because I'm doing a two-sided test, I want to do a 90% confidence interval, and that's going to give me basically 5% on both sides, which would give us altogether like 5% on both sides would give us a 10% alpha level altogether. All right, so then hit calculate. So we would say that we are 90% confident that the true proportion is anywhere between 17.93 and 31.19. Now, because 20% is actually contained in this confidence interval, that shows that we don't have enough evidence. We believe that it actually could be. It could actually still be 20%. So we're looking for a confidence interval that's entirely above or entirely below, or in other words, where the hypothesized proportion P naught is not contained within that confidence interval. All right, so let me show you the difference between the two methods. Okay, so one, we're calculating a p-value from a hypothesized. The other one, we use the sample and then we calculate from the sample a confidence interval. So if we're calculating a p-value, which is what we usually do with a test, we are basing it off the sampling distribution model, assuming that the true proportion is 20%. So that's what our p naught and our q naught, and that's the standard deviation for the sampling distribution model based on the p naught, which is the hypothesized proportion. Okay. Now what's different is if we are basing it off of a confidence interval, then remember confidence intervals are trying to guess the true proportion, which so we're not assuming the true proportion is 20%, we're trying to guess or estimate what that one is by using a confidence interval. So we center it about our sample proportion, which is 25% or 24.6. And so we're using p hat and q hat, so we have 25 and 75. Now notice just because a slight difference between these two values, even if it's only off by like 4.6% or whatever, it still changes our standard deviation. So that's why we call this the sampling error instead of standard deviation. So this is the standard error because it's based on the sample proportion, which we know is not the true proportion because samples vary, especially really small samples, they vary a ton, right? So that's why we annotate this standard deviation. This one is standard error because it's based on the sample, which we know is not correct. Okay, so then from our centered at 25%, if you notice that's here, that's within, actually it's going to be slightly just left of the 10% because we had about 11% on both sides. Okay, so centered here, which is our best guess, and if we go out 10% on both sides, which would be 80% confidence, even that one would contain the actual true proportion of 20%. Whenever we went out a 90% confidence interval, which had 5% on both sides, then it absolutely contained the 20%. And that's what we saw in our confidence interval. Okay, see how it goes out here to about 17% and contains the 20%. So because it contains the 20% and the true proportion is captured within the confidence interval, we don't have enough evidence to be able to conclude that. So an alpha level of 10%, basically doing a 90% confidence interval. If it's two-sided, then we were able to we failed to have enough evidence to reject the null hypothesis, so we had to stick with the null. All right, so remember the p-value is a conditional probability based on the sampling distribution model and the assumption that the null hypothesis is true. That's essentially what we're doing on the top part here. Okay. A two-sided alternative is whenever we're interested in it being either direction, either above or below the actual hypothesized value. So it's just simply saying the true proportion is not equal to the null hypothesis, or is not equal to the hypothesized proportion. So whether it goes up or down, it's just changed. That's what we're interested in. One side is when it's strictly greater than or less than. So it's a one-tailed or one-sided test because we're only interested in going in one direction instead of both directions. All right, number 9, better than aspirin. A very large study showed that aspirin reduced the rate of heart attacks by 44%. A pharmaceutical company thinks they have a drug that will be more effective than aspirin and plans to do a randomized clinical trial to test the new drug. Write a null and alternative hypothesis. So if aspirin reduces the rate of heart attacks by 44%, and the company is claiming that their drug reduces it by more than 44%, our null hypothesis is going to be that there was no change or that it was not effective. So it would be that the drug does not reduce heart attacks by more than 44%. It's no better than aspirin in that case. So basically we're assuming innocent until proven guilty. So that would be that the proportion is still 44%, meaning that the new drug is not more effective than aspirin at reducing the rates of heart attack. The alternative is not going to be two-sided. It's not just that it's not 44%. We're only interested in if it it increases if it reduces the rate of heart attacks by more than 44%, so that it outperforms aspirin, in other words. So we're only interested if the new drug reduces the rate of heart attacks more than aspirin, which is that the true proportion is greater than 44%. They conducted the study and found the group using the new drug had somewhat fewer heart attacks than those in the aspirin group. Okay, so that's good. It's in the right direction, but the p-value for the hypothesis test was 28%. So meaning it was only in the top 28 percentile of the sampling distribution model if it was still 44%, which is not going to be it's not going to be enough evidence. So that's not enough proof in order for us to be able to reject the null hypothesis. So that could have occurred by chance. It's too common. Our p-value, the probability of this occurring, is too high, in other words, for us to be able to conclude that it is more effective. So we fail to reject the null. So with such a high p-value, we fail to reject the null hypothesis, which is that the true proportion is still 44%. So it's not any more effective than aspirin. So there's either two things. We either need to do a larger study in order to increase the power, or it's just that the effect size is not big enough for us to be able to detect it with such a small sample size. What would you have concluded if the p-value was, okay, so if the p-value is less than 1%, then that's going to be more significant than any reasonable alpha. So that would be very, very rare, and we'd be able to reject the null hypothesis in favor of the alternative. So with a p-value lower than any reasonable alpha level, even 1%, okay, which is like the strictest alpha we usually would use, then we have enough evidence to reject the null hypothesis in favor of the alternative that the true proportion is actually higher than 44%. All right, 15-ish, absentees. So this is a similar problem to the one that's number 15 in the book. The National Center for Education Statistics monitors the aspects of elementary and secondary education nationwide. In 1996, numbers often used as a baseline to assess changes. In 1996, 34% of students had not been absent from school even once during the previous month. So 34% had perfect attendance throughout the last month. In the 2000 survey, the response from 8,302 students showed that the figure had slipped down to 33%. So even fewer had perfect attendance in the last month. Officials would, of course, be concerned if the student attendance were declining. So our sample proportion is lower than the actual hypothesized proportion from 1996, but is it low enough? Is that enough evidence for us to be able to say that it's gone down? Now, with such a high sample, so a large sample size, this might actually be statistically significant, even though a drop in 1% of attendance is not, over the course of 4 years, would not necessarily be considered practically significant. It would still be considered statistically significant. Maybe. We'll see. We got to calculate the p-value. All right, do the figures give evidence of a change in the student's attendance? All right, so let's write our hypothesis. So our null hypothesis is that there's no change and that it's still 34%. The alternative, we're only going to be interested if it's dropped. So it's a one-sided test where the p-value is, where the proportion is less than 34%, which is to say that the absent rate has been reduced. Check the necessary assumptions. So was this a random sample? Said they surveyed 8,302 students. If this is coming from the National Center for Education Statistics, you would expect that they would do it right, but they didn't mention how they surveyed. It could have been a convenience sample. They could have gone to schools and then just surveyed a bunch of kids at the school. But the problem is all the kids that aren't at school wouldn't be a part of that survey, and so it would kind of bias it towards making it look like the attendance rates were even higher. So there's some pitfalls that we'd have to make sure that we don't avoid. Make sure that we avoid. 10% condition, we are sampled without replacement, but there are definitely more than 83,000 students nationwide. So this is national, so no problem there. Success failure, with such a large sample, of course, 33% of that, we definitely had more than 10 students who were absent and 10 students who were there for the whole month. Create a confidence interval, one proportion z-interval to test the hypothesis with an alpha level of 5%. All right, so let me go back to our numbers here, and I'll put this in the calculator. So we want to do a test here. So we're going to go to stat, arrow over to test, and I'm going to do a confidence interval. So one proportion z-interval. The number that we had was 33%. So I'm going to put that in as a percentage. So 33% of 8,302, and then that's going to be a decimal. I need to change that, so I got to round it back up because it was rounded in the first place. So that means we believe there were 2,740 students that had perfect attendance out of a total of 8,302. Let me fix that, 8,302. There we go. If we wanted to have an alpha level, so I have to go over to this slide, an alpha level of 5%, that means I need to have 5% on one side of my confidence interval, which means I got 5% on the other side. So in the middle, my confidence interval is 90%. So I'm going to do a 90% confidence interval and then hit calculate. Okay, so our interval is that we are 90% confident that the true proportion is between these two values. So explain it in context. So we're 90% confident the true proportion at least in 2000 for the attendance rate is somewhere between 32 and 33.8%. So is it possible, based on our confidence interval with an alpha level of 5%, is it possible that it's still 33% or still 34%? Because that was our assumption. Yeah, 34%. Well, because 34% is not contained within the confidence interval, then we have enough evidence to say that we believe that it's lower than 34%, right? So we would say that since the hypothesized proportion is not contained in our 90% confidence interval, we can reject the null hypothesis in favor of the alternative, which is to say that the true proportion in 2000, the attendance rate, has actually gone down. Now, how much has it gone down? Well, we believe it's somewhere between, with 90% confidence, we believe it's somewhere between 32 and 33.8%. Now, is that statistically significant? Apparently it is with such a large sample size. Is that practically significant? If it's only decreased anywhere from 0.2% all the way to 18 point or 1.8%, that's not necessarily what I would consider practically significant. So that wouldn't really concern me, but maybe it does someone else. So statistically significant, yes, it has gone down, but is it enough to cause worry? That's up to you to decide whether it's practically significant or not. Let me know if you have any questions, and I'll see you guys later.